let's go through and get this stuff down. How is a vector different from what we've looked at before? So those of us that have taken physics, what is a vector? It's a magnitude and a direction. So it's a mathematical quantity. Now before, when we just say the number 5, it's a magnitude, it's a size. A vector is something that combines a magnitude and a direction. So I will put it down as a mathematical quantity. That word magnitude. Magnitude meaning size. So common times when you see vectors, when vectors are used in your daily life, you listen to the weather report and they say the wind is blowing at 15 miles per hour north by northeast. So common example, wind. You're going at 15 miles per hour. I will use some notation like north. I'll make that 70 degrees east. Size, direction. So numerically we can represent them by actually describing, giving a number to the magnitude, to the size, how much it's blowing, how much it's pushing, the distance in one direction. You go and you walk 5 miles due east. You push with a force of 16 pounds down. You've got a size and you've got a direction. So that's what's different before. Before it was just size. Now it's size and direction. So we've got a special name for that when it's just a magnitude. Physics, S word, do we know it? Scalar, all right. A scalar is a number that is just a magnitude. So 7 apples. 7 of them. Just a quantity. Leads us to the joke. I suppose jokes are always made worse when they are math related and you have to say they're a joke. What's the difference between a mountain climber and a mosquito? One's a scalar, one's a vector. Mountain climber is a scalar, it climbs up the mountain, it scales. A mosquito is a vector in disease terminology. A vector is a means of transmitting a disease. So, most math jokes need an explanation to those the uninitiated.
Related to a shark. I like sharks.
Related to a shark. I can't do that. Okay, so we've got a vector. We can represent them numerically. 15 miles per hour north, 70 degrees east. We can represent them geometrically. And because we've got a direction and a magnitude, we often represent these on the coordinate plane. Doesn't actually matter where we start them on the coordinate plane, but we've got a direction. So that last one, if I say 15 miles per hour north, 70 degrees east, are we familiar with bearing notation? Okay, we'll talk about that. What this means is the size of my vector is 15, and I'm going up. In terms of bearings, we know north, south, east, west. Going around the compass rose. North is at top. So if you've ever read a compass, used a GPS unit, alternative lifestyle activities, whatever you do in gym, lifetime activities, we know what a compass is? Yeah. Alternate environmental activities. Okay, I don't know what it's called. We know what a compass is? Not the draw circles compass, but a directional compass. Compass, compass. Compass. It's a means of finding directions. We say north is 0 degrees, east is 90 degrees. It takes our 360-degree system and puts it onto a circle. South is 180 degrees, west is 270 degrees, and then we go around to 360, but 360 is just it. So this is finding directions. Sometimes we say we are following a heading or taking a bearing. So this is terminology that we will use that is common in orienteering. We know what orienteering is. Orientation, finding your way around. Orienteering is a sport, is an activity of using a map and compass to find your way around.
That's a sport.
It is a very competitive sport. Not at this school, I don't believe. It used to be an Olympic sport. What's this? We could form an orienteering club. It's been a while since I've been deeply involved with orienteering clubs. There is an orienteering merit badge that I used to teach. Using a map and compass to find your way around. Orienteering on its own is a problem-solving activity, how to get from point A to point B. When we are using a compass, we follow headings, we take bearings. It gives us a direction, but we've got north, south, east, and west. They go in that order. North, south, east, west. Look, it spells we. Know your directions. Never eat soggy waffles. Okay, that works. I always had never eat shredded wheat because that's what we had before. Our notation, if we want to represent a vector, 15 miles per hour, what I'm going to use is a ray. Think back to geometry. I'm going to use a ray. We remember the definition of a ray back in geometry.
Yeah, point.
It goes in one direction.
It has one endpoint, and it goes in one direction. It's called a directed line segment. So it has a start and it has a direction. So array, it has a start and it has a direction. There's a ray. So we want to represent a vector 15 miles per hour. So the length of my vector would represent the magnitude. So if we have different length arrows, different length rays, it represents that one is longer than another. North 70 degrees east. The way we represent this, we start going north, and then I'm going to go at an angle 70 degrees away from north. So north 70 degrees towards the east, it's going to be about there, and I'm going to draw that. That's going to represent a vector of 15 miles per hour. So that is going to be 15 north, and we went 70 degrees to the east. Put my units in there. I'm going to call that 15. It depends upon the scale. If you have like a coordinate plane or a grid on there, you can match it up. Pass that back, please. So likewise, thanks. If I say I've got 5 miles per hour at north 20 degrees west, I'm comparing 15 to 5. Well, 5 miles per hour is 1/3 the magnitude of the other one. So my vector would be 1/3 the length. So the length matters. Length matters here. It gives us the relative size of the vectors. So 5 to 15, this is 1/3. I would draw it at 1/3. Well, north 20 degrees west Well, I would start north and I would go at an angle 20 degrees to the west. That's about a third, right? It's about a third. So there's an angle. There's 20 degrees north, 20 degrees to the west. It's about 1/3 the length. So by drawing it this way, it gives us the visual representation that one has a greater magnitude than the other. That is an important characteristic of vectors. So I will write that down. We're going to, when graphing, length is proportional to the magnitude. So far, so good. That way, even if we don't have numbers, if we are just representing things geometrically, we can draw them out. I'm going to say, here's vector A. I'll represent that with a little arrow over the top over it. I'm going to say here's vector B. I'll represent that with the letter indicating the name of my vector. I'll put a little arrow over the top of it just to say vector. Comparing these two, vector A, vector B, what's your vector, Victor? We know the movie?
Airplane.
Okay, good. Airplane. Go watch it. Which vector has a greater magnitude? B. Okay, it's a longer vector and it's bigger. We can represent this. Now I used bearing notation and magnitude. We could represent this with just our typical means of measuring angles, where 0 degrees or 360 degrees is here. Back to our regular coordinate plane when we have an angle in standard position. And so we could say A, all right, how long does that look? 5 units. And it's going, so vector A is 5 units at, what's that angle?
30.
At 30 degrees. So not using our bearing notation, or I just give an angle. And then we can also compare that vector B. If vector A is 5, what does vector B look like? 10. In terms of magnitude, you got the angle. What's the angle all the way around there? 240 degrees maybe. We have an angle in quadrant 3. So going back to our unit circle, or just recognizing our angles going around the coordinate plane, 0, 360, well, that would be 90 degrees. That would be 180 degrees. This is 270 degrees. All the way around is 360. Notice it's different when we talk bearings. If we put on there north, south, east, west, never eat soggy waffles, 0 degrees is top. So when you're walking straight forward, 0 degrees is towards the top. Yes, that's going to be a little bit confusing, but be careful about that. Just watch out. If we are talking about direction and using bearing notation with north, south, east, west, 0 degrees at the top. If we are not using bearing notation, if we're just using an angle measurement, 0's to the right. It flops over. But we can have vectors go in the same direction. Now just to emphasize that size, the length of the vectors is proportional. If I draw 2 vectors, vector C, vector D, they're going in the same direction. So we could have vectors going in the same direction. And here's where the length of the arrow really matters, because it shows the difference in the size. And D, I'd say again, is about twice C. Now, the way I've drawn these so far, or the example using the bearing notation, I've started my vectors at the origin on the coordinate plane. I've started my vectors at the origin on a coordinate plane. Vectors do not have a set starting point. Vectors do not need to have a set starting point. We commonly use a coordinate plane and the origin just for convenience. Say it's wind is traveling in this direction, whereas you might be flying or walking in this direction, or a force is applied in this direction and a force is applied in this direction. But vectors need not have one set starting place. So I can put, just for argument, we can have a vector on a coordinate plane, and I can look at other vectors there. I would say that 5 vectors that I've drawn down here, I could even say 1 unit, 45 degrees for that one right in the middle. But all 5 of these, if we look the length of them, they're all the same length, so they're all the same magnitude. And if we look at the direction of them, well, they start and then they go up to the top right. So each one starts at a point and goes up to the top right. So they all have the same direction.
For the vectors, are we using protractors or like, are we just like eyeballing it like the same way?
For the most part, for convenience, we're going to eyeball them. If we want to be accurate, we should use a protractor. But for time and convenience, I'm just going to eyeball them. These are all going in the same direction. So those 5 are all actually the same vector. They're all equal vectors. So vectors are equal when we have the same size, the same magnitude, same direction. Now that word magnitude, size, I'm going to use those interchangeably. So all 5 of those are equal vectors. Doesn't matter about the starting point. So good. Now, common uses, physics, navigation, any time when forces are exerted. Now, if we look at some navigation examples, you know how fast a plane flies? 50 miles an hour? Oh, 500 minutes. I say 50, I could run faster than that. Almost. Well, like at one split second, maybe I could go like 50. No. So plane flies at 500 miles per hour. So we can consider a plane is at Bradley Airport, north of Hartford, and it wants to go to Boston. Is Boston north, south, east, west? Where is Boston relative to Bradley? It's to the northeast. It's actually, so if Bradley's over here, Boston's probably over here, maybe not even that much. Say we're starting at Bradley, we want to fly to Boston. I don't know why we wouldn't just drive. We have to spend 2 hours waiting in line at the airport, or we could drive 2 hours there. But we're going to fly east 10 degrees north. So plane flies 500 miles per hour, east 10 degrees north. So north, east, south, west, reading the bearing notation, east 10 degrees north. So we start off going towards the east, and I'm 10 degrees up towards north. So I'd have a vector that looks like that. That would be our plane. Here's our plane. So we've got 10 degrees, and that represents 500 miles per hour. Now wind blows. Wind blows, there's a B in that. Wind blows 50 miles per hour. We are quite a strong gale. We are going south 15 degrees west. I've got a magnitude, I've got a direction. Well, how long is my vector for the wind going to be compared to my plane vector? That's going to be a tenth. So, well, and we are south 15 degrees west, so south, and we're going to go 15 degrees towards the west. So we're going to have something that's about 1/10. We get that vector. That would be our wind vector. We're starting off south, and we move 15 degrees towards the west. About a tenth. Hard to draw since it's 1/10 the size, and I didn't draw it that large. Now the plane set on its course. We're going to Boston, east 10 degrees north, but the wind is blowing. That's going to change the direction of the plane, right? So how could we figure out the actual direction of the plane? We have to add those two vectors. What's the actual trajectory? We need to add our vectors. Put an exclamation point there. So we're going to have two methods of geometrically adding vectors, two methods to geometrically add vectors. And when I say geometrically, I mean in terms of the graph, the length and the angle. Two means of geometrically adding vectors. All right, that red marker's on its way out. First is what we call the parallelogram method. Parallel.
Oh, there's one R.
There's only one R.
No, there's two R's.
No, there's not.
One,
Yeah.
two.
Well, R.
There are two R's, not three R's. Okay, parallelogram. Okay, there's only one.
That's your whole area.
No, really not. Parallelogram method. So when we've got two vectors, we share the same starting point. What I will do is I will take each of the vectors and I will transpose them, finish off a parallelogram. So I'm going to take one vector, add it on the other side. Take the other vector, add it to the other side. Make a parallelogram. The sum that we call the resultant. Resultant. It's what results from adding. Is going to be the vector from one diagonal starting at the originating vertex, and it's going to be the diagonal to the opposite vertex. So the parallelogram method, we start our vector at the originating vertex, and we draw the diagonal to the opposite vertex. That is going to be our resultant vector. That is the sum. So geometric. Yep.
The actual trajectory would then be the degrees, the total degrees.
It's not quite. It's going to be a little bit different. We have to do a little bit of computation to figure out the angles in there. So it's not just adding the degrees. So if we take this example up here and use the parallelogram method. I would take the blue wind vector and I would add it onto the end. I would take the black plane vector, add it to the opposite side, and our resultant, the sum, is going to be starting at the origin and going towards that opposite vertex. So that orange section right there, that would be the actual trajectory, the actual direction the plane flies. So if they're heading in one direction, so the engines are pushing here, but then the wind is blowing them down, that's where we end up. So here's why drawing vectors proportionally actually is important. Because if we draw the wind at the same length, the wind at the same length is going to put our trajectory way out of the way. So by drawing them proportionally and using appropriate angles and measurements, we can create a parallelogram to geometrically visualize the resultant, the outcome of where we would go. So that's one method, the parallelogram method. Now what we see is, well, this vector is just repeated here. This top vector is just repeated here, and we've got a diagonal. Well, if we take the vector that we are adding, so we've got plane vector and wind vector. What we're saying is we've got the plane vector plus the wind vector. The wind vector is just the repeat there. And it doesn't matter where we start. It doesn't matter where we start. So what I can actually, my second method is called the tip to tail method. Tip to tail method. So if we have our two vectors, there's the first one that we have. I will begin the second vector at the tip of the first. So I want to add the wind vector. I'm going to take the wind vector and put it, I'm going to start it right at the tip of the original, the first vector that we're adding. And the resultant is the third side of that triangle. It will be exactly the same thing. So if we're adding vectors, the start one, we can go down the length of one, pick up with the next one, and so forth if we're adding multiple vectors. Remember back to elementary school field days and tug of war? Do they still do that when you were in elementary school? Field days?
Yeah.
Okay, that wasn't yet forbidden. That it promoted competition and collaboration. Tug of war! Still have recess back then, right? Okay, do they still have recess now? I hope so. I think we should have recess in high school. I think it's called lunch, though. I think you should have lunch in high school, too.
You need some fresh air.
Tug of war! You've got one group pulling horizontal. You've got another group pulling horizontal. We've got a force that we're pulling in opposite directions. Team A, Team B. These are the vectors representing our tug of war. Who's going to win? A. If we've got a three-way tug of war. And there's Team C. Where's that rope going to go?
Straight between C and A. No.
Are they equal?
It's going to be closer to C than A.
Between C and A? Well, we've got A plus B plus C. I could take vector A. We are adding the magnitudes and the direction. So A, there's A. Using this tip to tail method, if we add B, adding B brings us from there back to there. There's B. And then C, there's C. Resultant from the start, from the origin to the end, if we follow. From tail to tip, from tail to tip, from tail to tip. There's our final outcome. I'm going to use V for vector. So we can add multiple vectors. What was it?
Now you can transpose the blue line onto the resulting vector onto the original graph.
We can take that back. Actually, I'd have to go all the way up there. There it is. What if we have two vectors being pulled in the same direction? Or actually, if I take so A plus B. So if we start at the origin, we go A. That is this length in this direction, towards the right. B is this length to the left. So A plus B is B will go this distance to the left. It would be, in a way, you're subtracting because you're pulling in opposite directions. They cancel each other out. So you're pulling in opposite directions. They cancel each other out. How about if we have two vectors that are completely opposite? They would not move anywhere. They would be at what we call equilibrium. So we've got opposite vectors. So if we have negative V, that's just the opposite of V.